The universe as a neural cosmos, an analytical comparison of cosmic and cerebral dynamics. Introduction. A fractal analogy at cosmic scale. The human brain, with its approximately 86 billion neurons forming trillions of synaptic connections, stands as the most intricate structure known within the observable universe. Yet, when cosmologists map the distribution of galaxies across billions of light-years, revealing clusters, superclusters, vast voids, and filamentary walls, the pattern eerily mirrors neural networks visualized under electron microscopy. This is no superficial resemblance. Both systems emerge from self-organizing principles that operate across 40 orders of magnitude, governed by forces that sculpt complexity from chaos. This essay examines the structural, functional, informational, emergent, and philosophical parallels between the universe and the brain, weaving evidence from cosmology, neuroscience, systems theory, and information physics into a unified framework. The comparison is not poetic metaphor but a convergence of universal algorithms for complexity. Structural isomorphism, filaments, nodes, and voids. At the largest scales, the universe organizes into a cosmic web, galactic filaments akin to axonal bundles, superclusters resembling cortical columns or thalamic nuclei, and cosmic voids echoing ventricular spaces or white matter lacunae. Surveys like the Sloan Digital Sky Survey and the Euclid Space Telescope have mapped this structure with unprecedented precision. A 2020 study in the Astrophysical Journal by Susskind et al. Applied persistent homology, a topological tool originally developed for brain connectomics, to quantify the cosmic web's architecture. The result? Both systems exhibit scale-free, small-world topology. In the cosmic web, approximately 100 billion galaxies form the nodes, linked by roughly 10 to the power of 16 gravitational interactions. In the human connectome, 86 billion neurons are interconnected by 10 to the power of 14 to 10 to the power of 15 synapses. Both networks show power law degree distributions, a few hubs dominate connectivity, high clustering coefficients, triadic closure is common, and short average path lengths, typically 2 to 3 steps between any two nodes. This means that a galaxy in the Virgo supercluster is gravitationally linked to one in the Laniakea supercluster through just a few intermediaries, just as a neuron in the visual cortex communicates with one in the prefrontal cortex via a handful of relays. This structural convergence arises because both systems are self-organizing critical systems. Gravity drives cosmic clustering, while electrochemical gradients and synaptic pruning shape neural architecture. The outcome is statistically indistinguishable network geometry, suggesting that the laws of complex systems transcend scale. Functional parallels, information processing and dynamics. Signal propagation and criticality. Both the brain and the universe operate at the edge of chaos, near critical points where small inputs trigger cascading, power law distributed events. In the brain, neuronal avalanches recorded via multi-electrode arrays follow power law size distributions, as demonstrated by Beggs and Plenz in 2003. This criticality optimizes information transmission, dynamic range, and computational flexibility. The universe displays analogous behavior. During the recombination era, redshift z approximately equals 1100, tiny density fluctuations, Dr. Rho approximately equals 10 to the power of 5, in the primordial plasma grew through gravitational instability into today's cosmic web. The evacuation of voids and condensation of filaments mirror neural cascades during learning or epileptic seizures. A 2023 paper in Physical Review X by Fosco et al. Used renormalization group methods to show that the gravitational action in the early universe and the Ising model of neural firing belong to the same universality class near criticality. The mathematics of phase transitions unite star formation and synaptic strengthening. Memory and holography. Memory in the brain is distributed and redundant. Carl Lashley's principle of equipotentiality, demonstrated through lesion studies in rats, showed that no single region holds a complete memory. Engrams are encoded across widespread cortical networks. Damage degrades but rarely erases recall. The universe encodes its history similarly through the holographic principle, proposed by Gerard T. Hooft and Leonard Susskind. The information content of any volume is stored on its boundary surface, not within its bulk. Black hole entropy scales with surface area, a 4L_p squared, not volume, a principle that mirrors how neural memory capacity depends on synaptic surface area, not neuronal volume. The ADS-CFT correspondence in string theory formalizes this duality. A higher dimensional gravitational theory is mathematically equivalent to a lower dimensional quantum field theory on its boundary. In neuroscience, integrated information theory, IIT, by Tononi and Koch, 2015, proposes that consciousness emerges from irreducible cause-effect structures within neural networks. These structures may be topologically isomorphic to spacetime itself, suggesting that information processing is a fundamental property of geometry, whether synaptic or cosmic. Informational entropy and thermodynamic arrows. Both systems are far from equilibrium thermodynamic engines that locally reduce entropy by exploiting energy gradients. The brain consumes about 20 watts to sustain 10 to the power of 15 synaptic operations per second, generating ordered electrochemical patterns while dissipating heat. The universe, cooling from 3000 K at recombination to 2.7 K today in the cosmic microwave background, uses gravity to cluster matter. Star formation, black hole accretion, and supernovae are the cosmos's synaptic events, converting gravitational potential into radiation and structure. A provocative 2024 study in Nature Physics by Vladimir Vanchurin modeled the universe as a learning neural network. Using statistical mechanics, Vanchurin derived fundamental constants from network dynamics. The Planck constant h emerges from synaptic weight updates. The speed of light c arises from information propagation delays. The gravitational constant g reflects network regularization. Though speculative, the model reproduces general relativity in the classical limit and suggests that cosmic evolution is a form of computation, a gradient descent on a universal loss function. Emergent phenomena. From quarks to qualia, from plasma to perception. Phase transitions. Both systems undergo dramatic macroscopic phase transitions. In the brain, sleep-wake cycles, anesthesia, and seizures represent collective shifts in neural dynamics. In the universe, recombination, plasma right-pointing arrow neutral gas, galaxy formation, diffuse gas right-pointing arrow bound structures, and hypothetical grand unification transitions at 10 to the power of 16 JV mirror these state changes. Self-similarity and fractals. Benoit Mandelbrot's fractal geometry applies equally to both domains. Dendritic branching in neurons exhibits a fractal dimension d approximately equals 1.4-1.8. The cosmic web, up to scales of approximately 100 megaparsecs, has a fractal dimension d approximately equals 1.8-2.0, consistent with cold dark matter simulations. This self-similarity implies that iterated growth processes, whether biological or gravitational, follow universal mathematical rules. Philosophical and ontological implications. Panpsychism or computational monism? If the universe is a neural network, then consciousness may be a multi-scale phenomenon, from planetary cognition to galactic qualia to cosmic awareness. The hard problem of consciousness, why physical processes give rise to experience, dissolves if spacetime geometry is the substrate of experience. The fine-tuning problem becomes a selection effect. Only universes with critical neural architectures support observers. The simulation hypothesis reframed. Nick Bostrom's simulation argument posits advanced civilizations running ancestor simulations. The brain-universe analogy suggests a deeper recursion. The universe simulates itself. Brains model the cosmos contains brains. This self-referential loop resembles a Quinning structure in Gödelian logic, reality referencing itself. Empirical tests and future directions. Several testable predictions emerge. The Cosmic Connectome project used the Square Kilometre Array (SKA) and Large Synoptic Survey Telescope (LSST) to map the local universe (ZNLT) 0.1 at neuron-level resolution, applying Human Connectome project graph metrics. Criticality signatures. Search for power law distributions in fast radio bursts (FRBs) and gamma-ray bursts (GRBs), analogous to avalanche statistics. Quantum links. Investigate whether vacuum fluctuations in synaptic clefts, Casimir effect, correlate with CMB anisotropies, testing ideas from Penrose and Hameroff's OR theory, though controversial. Conclusion. A universe that thinks, a brain that expands. The universe and the human brain are not merely analogous, they are homologous expressions of universal complexification algorithms. Gravity sculpts galaxies as synaptic pruning sculpts cognition. Dark energy drives cosmic expansion as neuromodulators drive plasticity. The cosmic web is not a passive scaffold but a thinking lattice, its filaments transmitting gravitational waves as axons transmit action potentials. This convergence upends anthropocentrism. The brain is not a microcosm within the universe, it is a fractal echo of cosmic intelligence. As John Wheeler observed, we are participators in bringing into being not only the near and here but the far and long ago. The universe does not merely contain minds, it is mind, at every scale. To study one is to study the other. The next scientific revolution will not split atoms or sequence genomes, it will map the cosmic connectome and decode the syntax of reality itself.